Hello, everybody. So, week 14, session 2. I hope you are doing well. So, in this actual lecture, we continue chapter 9. We started the gas power cycles in previous lecture, and then you saw that we discussed the ideal cycle, Carnot cycles, and actual cycles. So in chapter 6, you learn about the Carnot cycles. Carnot cycles are both internally and externally reversible, and then we use, the Carnot cycle to get the maximum efficiency, for, some cycles. In this chapter, you learn about the ideal cycles. Ideal cycles are, internally reversible processes. So if you want to compare these two cycles, normally ideal cycles are more realistic models for actual cycles. So if we want to compare, in this chapter we use the ideal cycles to model the actual cycles. If you want to compare the thermal efficiency of ideal, Carnot, and actual cycles, Carnot cycles has the highest thermal efficiency, then ideal cycles, and eventually the actual cycles. If you want to increase the thermal efficiency of these cycles, I mean ideal, Carnot, or actual cycles, we need to increase the average temperature at which heat is supplied to the system, or we need to increase the average temperature at which heat is rejected from the system. Then we discussed the air standard cycle. So if you remember, for the heat, actually engines, we need to supply heat to the system, and then in this chapter, actually, we use a combustion chamber to supply heat to the system. So in this actually chapter, we use this air standard cycle. We assume that air actually is the working fluid, and we use this air standard assumption. Based on the air standard assumption, air is ideal gas. You can use the ideal gas equation state for the air, and we assume that all processes are internally reversible, and then we just cancel fuel. We assume that air is the only actually fluid in the process, and then heat is added from an external resource. Then we discuss the cold air standard assumption. So if you ask to solve a problem with the cold air standard assumption, you can use the specific heats of air at room temperature, or 25 degrees centigrade. Then we discussed the reciprocating engines. We discussed the bore, stroke, TDC, BDC, intake valve, exhaust valve, and then we discussed the compression ratio. If you remember, the compression ratio is actually the ratio of two volumes, but not pressure. So it's actually the ratio of Vmax over Vmin. Then we define the mean effective pressure. It's a fictitious pressure, and then based on the definition, the mean effective pressure is the W net over Vmax minus V mean. So we can use the MEP to compare the performance of several reciprocating engine with the same size. So the higher MEP means the higher actually W net. So we prefer to select engines with the same size and higher MEP. So then you saw that we have two types of reciprocating engines. We have the spark ignition or compression ignition. So in spark ignition, normally combustion start with a spark plug, and then with the compression ignition, normally combustion start with the compression. So we increase the pressure, and then temperature increases, and then temperature goes beyond this beyond the self ignition temperature, and then combustion reaction starts. So for the first actually type of reciprocating engine, we normally use the Otto cycle, and then for the second one we use the diesel cycle. And then you saw that for four-stroke cycle, actually four-stroke cycle includes 4 stroke and 2 revolution per cycle, and 2 stroke cycle includes 2 stroke and 1 revolution per cycle. Now let's go over the Otto cycle. What is the Otto cycle? Otto cycle is the ideal cycle for spark ignition engines. So meaning that the Otto cycle is internally reversible because it's the ideal cycle. So it has actually 4 stroke and then 2 revolution. The 4 strokes are intake stroke. In intake stroke, fuel and air are added to the piston, to the cylinder, and then there is a compression stroke. Fuel and air mixture are compressed, and then the power or expansion stroke due to the ignition and combustion reaction, the actually piston moves downward, and then we have the expansion, and then the last one is exhaust stroke. So let's watch these 2 short videos for the Otto cycles, and then we can just continue our discussion about the Otto cycles.
A basic lesson in the fundamentals of a 4-stroke EFI gas engine may be helpful to your understanding of Mercury products. Here are the basic components of every 4-stroke gas engine: a piston, a connecting rod, a crankshaft. As the piston travels up and down in the cylinder, this lateral motion is turned into a rotating motion at the crankshaft. The longer the stroke of the piston, the larger the displacement of gas and air occurs in the cylinder. To propel that piston, we need to ignite a tiny bit of gas and a whole lot of air. This creates expansion inside the cylinder. The fuel delivery system consists of an air intake manifold, valves, intake and exhaust, a fuel injector, and a spark plug. A 4-stroke engine is called a 4-stroke because 4 up and down motions are needed to complete the cycle. In the first stroke, the piston travels downward as the intake valve opens and a mixture of air from the atmosphere and a metered amount of gas from the electronic fuel injector enter the cylinder. This is called the intake stroke. On the second stroke, the piston travels upward, compressing the air and fuel to make a highly combustible mixture. This is called the compression stroke. At this point, the spark plug fires, sending the piston downward from the expansion of the air and gas mixture. This is the combustion stroke. The fourth stroke is the exhaust stroke. As the piston travels upward, the exhaust valve opens to release the burned air-fuel mixture. When the piston reaches the top of this stroke, the intake valve opens and the cycle begins all over again. It takes 1 up and down motion or 2 strokes of the piston to create 1 revolution of the crankshaft. RPMs, or revolutions per minute, is how many times the crankshaft rotates within that minute. At wide open throttle, the crankshaft may turn at 5,000 RPMs, or a dizzyingly 83 times per second. Meanwhile, the piston traveled up and down 166 times in that same second. Want to see how fast that is? Now, that's fast. Let's see it again. Amazingly, the 4-stroke EFI engine does this smoothly, quietly, and reliably for years and years of operation.
Okay, let's watch the other one. This one has, basic information about the Otto cycle.
The Otto engine is a combustion engine and is considered to be a technological milestone of human sort. It was named after its inventor, Nicholas August Otto. Otto engines were used in motorcycles, cars, and other vehicles. This animation explains the Otto engine as a 4-stroke engine. This engine is composed of a piston that moves up and down in a cylinder. The highest point the piston can reach is called top dead center. The lowest point it can reach is called bottom dead center. The volume between both points is called engine displacement. The piston is connected to the crankshaft through the connecting rod. The crankshaft transmits the rotational movement to the gearbox and consequently drives the wheels of a car or motorcycle. Two camshafts are installed on top of the cylinder, which control the intake and exhaust valve. The camshaft is connected to the crankshaft through a belt. More often than not, the crankshaft to camshaft gear ratio is 2:1, which means that for every 2 revolutions of the camshaft will rotate only once. An Otto engine has a spark plug that uses an electric spark to ignite the fuel charge. A 4-stroke Otto engine is an internal combustion engine in which the piston completes 4 separate strokes. The first stroke is called intake stroke. Here, the intake valve is opened by the rotating cam. The air-fuel mixture is sucked into the cylinder. The second stroke is the compression stroke. The intake valve is closed and the air-fuel mixture is compressed to a high degree by the piston. The higher the compression ratio, the more mechanical energy the engine can squeeze from the air-fuel mixture. Higher compression ratios, however, make self-ignition more likely. The third stroke has been named power stroke because this is the process where power is produced. The air-fuel mixture explodes. The force created by the explosion causes the piston to move down. The fourth stroke is called exhaust stroke. In this stage, gases remaining in the cylinder are removed from the cylinder through an exhaust valve. The crankshaft transmits the rotational movement to the gearbox, and the driver can drive. Often, engines of today feature more than one cylinder to power cars or motorcycles in order to increase speed and smoothness.
Okay, so yeah, here you can see the different steps of the actual 4-stroke spark ignition engine. So you can see that you have a compression stroke, power expansion, or combustion stroke, exhaust stroke, and intake stroke. So this is the actual one. For the ideal Otto cycle, so we assume that we have 2 isentropic, process, and also 2 constant volume process. So 2 isentropic steps and 2 constant volume steps. So this is the Pinot diagram for the ideal Otto cycle. So for the ideal Otto cycle, again, 2 isentropic steps and 2 constant volume steps. So for the ideal Otto cycle, first we assume that there is an isentropic compression. So air and fuels are, actually compressed. Actually, air, we assume that we have only air. Air is compressed. And then the second step, this is from 1 to 2, this is the isentropic one. For the second step, heat is added to the, system at a constant volume. So this is, a step 2 to 3. And then from step 3 to 4, there is isentropic expansion. So, and then the last one, at constant volume, Q is rejected, from the, system. So these are the 4 actually, steps of ideal Otto cycle. Now, please pause this video and then think 2 minutes. What do you think? What is the difference, the main difference between the ideal Otto cycle and actual, 4-stroke spark ignition engine? What is the shortcoming, with this actually, process with the ideal Otto cycle? Pause this video and think, about these, 2 different, cycles, and then just try to find, if there is any shortcoming in this, ideal Otto cycle. Okay, to answer this question, guys, let's just plot the TS diagram, for the ideal Otto cycle. So ideal Otto cycle has two isentropic or constant, entropy, steps, and then two constant volume, steps. So this is the TS diagram, for this, process. If you compare this actually, process with the ideal one, let's go back to the previous, it's like this one. If you compare, these two cycles, you can see that the the actual spark ignition engine has four strokes: one, two, three, and four. However, the ideal Otto cycle has only two strokes: one and two. Step two to three, the piston is, stationary, and then Q is added, at constant, volume. So step actually 4 to 1, the again the piston is stationary, and then heat is rejected at constant volume. So the actual, spark ignition engine has four strokes, while our model, the ideal one, has two, um, you know, um, stroke. So this is the main difference. So four stroke, two stroke. So how we can solve actually this shortcoming? So we can solve this problem if we add an intake and exhaust, stroke to this, process at constant pressure. How? Look, guys, this is the ideal Otto cycle, correct? If we assume that there is a, a step, the preliminary step to add air fuel actually mixture to the, this cylinder and piston at constant pressure. So there is a step 0 to 1, and then air and fuel mixture is added, to this, piston cylinder and constant pressure. So we move from point 0 to 1 at constant pressure. This is the pin diagram, correct? So piston moves from, actually the minimum, actually, volume to the maximum, to the Vmax, correct? This is the step 1, step 0 to 1, correct? Now, we have the isentropic expansion. This is the second stroke. Then heat is added at constant volume. There's no stroke here. And then the third stroke is, isentropic expansion. Then the fourth, actually, step at constant volume, heat is rejected. And then the fourth stroke is the, actually we assume that exhaust gases just leaves, this system at constant pressure or atmospheric pressure. So we move from point 1 to point 0. So there is a, actually compression, at this, step. So we move, actually, we have the fourth stroke. So if we assume these two actually extra steps, we can solve the problem, correct? So we have, now we have four stroke: one, two, three, and the four stroke. Now, question: okay, we solved the problem. Now we have four stroke. What happened for the W net? So we need to check if the W net changes. Look, guys, the W net for the ideal Otto cycle. Let's go back here. Yeah, for the ideal Otto cycle, the actually W net is area enclosed, by the, process, correct? This area is the W net. Now we need to check. We add two extra actually steps. So we need to check what happened for the W net. If the W net is constant, then we can accept these two, new or extra, steps, and then we can assume that the process has four strokes. Now let's check, the W net for this actually, step for process from 0 to 1, and then from state 1 to 0. For state 0 to 1, because the pressure is constant, and then this is the W boundary, you can write the W out from 0 to 1 equals the P naught, which is the atmospheric pressure, mu 1 minus mu 0. For the final step for the W from 0 to 1. This is the W in, and then this is again equals the P naught V1 or new 1 minus new 0. The point is that, guys, this is the W out and this is the W in, and the W in is negative, correct? We assume that the W is negative. So meaning that the actually net W for this step will be 0, correct? So meaning that the area of the the total actually work is constant, even with with addition of these two new steps. So what's the conclusion? The conclusion is that we can use the ideal Otto cycles with two isentropic as process and two actually constant volume process, correct? This is actually the two stroke, but we can assume that this is the four stroke, and then we can use it as a model for actual uh, you know um, Otto cycles. So we solve the problem, correct, by addition these two steps. Now, so we need to calculate the thermal efficiency of ideal Otto cycle based on the definition for the thermal efficiency. If you remember, the thermal efficiency is the desired output over required input. Here, the desired output is W net. What is the required input? The required input is Q E. So the thermal efficiency is W net over Q E. So for the W net, if you write the energy balance for this cycle, you can write the W net equals to the Q net. And then, the Q net equals to the Q in minus Q out. If you simplify, this actually term, you can write thermal efficiency is 1 minus Q out over Q in. So you can use this equation, guys, to calculate the thermal efficiency of all, ideal Otto cycles. You can use these equations. Now let's assume that we have the ideal Otto cycle with constant specific heats, correct? So this is valid for all cases, for all Otto cycles. If we assume that we have the ideal Otto cycle with constant specific heats, let's calculate the Q out and Q in for this process. If you want to calculate the Q in, correct, this one, you need to write the energy balance for process between state 2 and state 3. So if you write the energy balance, this is the closed system. For the closed system, you can write Q net minus W net equals the delta U. So here, process between point 2 to 3, is a constant volume process, meaning that the W net is 0. There is no boundary work because the volume is constant. Keep in your mind that the W boundary is P d nu. So the V nu is constant, so there is no W. So we can write Q net equals to the delta U. Here there is, for this step process between step state 2 and 3, there is no Q out, so we can write Q in equals to the M CV T3 minus T2. Again, I assume that there is a constant specific hits, or we can use the average specific hits. Now let's calculate the Q out. If you want to write the Q out, so please pause this video, guys, and then spend 2 minutes. Just find the and actually equation for the Q out by writing the energy balance for process 421. Okay, guys. Again, you can write the energy balance for closed system. You can write Q net minus W net equals the delta U. Again, the W net is 0 because volume is constant, so you can write Q net equals the delta U. Keep in your mind that here we have the Q out, Q in is 0, so you can write the Q negative Q out for the process between state 4 and 1 equals to the M CV T1 minus T4. And if you multiply this negative, we can write it T4 minus T1. Now let's substitute for the Q in and Q out from these two equations in the equation for the thermal efficiency. If you substitute, so we can cancel the MCV, in denominator and numerator. And then the thermal efficiency is 1 minus T4 minus T1 over T3 minus T2. And then you can rewrite it in this format, correct? So if you multiply the T1 in these parentheses, again, you will have this term. If you multiply the T2 in this parentheses, again, you will have this, term. Now, let's see if we can simplify, this equation. So look, guys, this is the ideal Otto cycle, correct? So, and then for the ideal, actually, Otto cycle, if you, sorry, not the Otto cycle. If you remember, guys, from the previous chapter, for isentropic process with constant specific heats, correct? For isentropic process with constant, specific heats, we can write, these equations. So isentropic process and constant specific heat. Keep in your mind that we have two isentropic steps. Step 1 to 2 and 3 to 4 are isentropic. So we can write these correlations, between the temperatures and volumes of actually, these two, states. Now, let's look at, these volumes. Let's look at the right side of these two equations. So what is the relationship between V1 and V4? If you look at, guys, this, TS diagram, the V1 equals to the V4 because this is a constant volume process. What's the relationship between V2 and V3? Again, V2 equals to the V3, correct? Because this is a constant volume process. So, meaning that the right side of these two equations are the same. So we can write T2 over T1 equals to the T3 over T4, or you can rewrite it in this format. So we can write T4 over T1 equals to T3 over T2. If you just look at, guys, this equation, you can see that you can cancel these parentheses in the numerator and denominator because T4 over T1 equals to T3 over T2. And then we can write the thermal efficiency of Otto cycle equals to the 1 minus T1 over T2. Keep in your mind that, guys, this is very important. This equation is valid for ideal Otto cycles with constant specific heats. If you are asked to solve the problem with the variable specific heats, or if you believe that the constant specific heat is not a good assumption, you are not allowed to use this equation. This equation is just valid for ideal Otto cycle with constant specific heats. And then so we can actually simplify, this equation. Again, so we know that the process 1 to 2 is isentropic process. So for the isentropic process, we can write the T2 over T1 equals the V1 over V2 K minus 1, isentropic process with constant specific heats. So what is the V1, guys? If you look at, this, process, you can see that the V1 is the maximum volume, the Vmax, and the V2 is the Vmin. Actually, the V1 over V2 is the R, compression ratio. If you remember, R compression ratio is the Vmax over V2. So we can write T2 over T1 equals to the R K minus 1. And then here we need the T1 over T2. So if you calculate the T1 over T2 from this, equation, you can write the T1 over T2 equals to 1 over R K minus 1. This is another equation, guys. If you have the compression ratio, you can use this equation to find the thermal efficiency of Otto cycle with constant specific heats. Now, question. We want to increase, the thermal efficiency, correct? So because the higher thermal efficiency means the higher W. So to increase the thermal efficiency based on this equation, we need to increase R and K, correct? The higher R means the higher thermal efficiency. The higher K means the higher thermal efficiency. So keep in your mind that the thermal efficiency of actual spark ignition engines is low. It's something between 25 to 30%. And then, yeah, this is the equation, correct? So based on this equation, we are interested in the higher, actually, the highest value of R. If we plug, guys, the compression ratio based on the thermal efficiency, normally there is an optimum value for the R, correct? Based on this equation, guys, we prefer to use the highest value, for example, 16, 20. But, practically, we use a compression ratio between 8 to, for example, 11. Why? Why there's optimum value, correct? Because the higher, compression ratio causes, to actually make temperatures which are higher than the, self-ignition temperature. So if we use the highest, the higher compression ratio, what happens? There will be, guys, the, early and local, actually, ignition or combustion in the, piston. So meaning that a part of the energy of, fuel is lost before we just have, the expansion, step. So keep in your mind that W net is actually generated during the expansion, correct? So if we have the early and, a local, ignition, what happened? A part of, the energy of fuel is lost. This is the first, drawback of very high, compression ratio. The other one is that when we actually have the local combustion, we have the temperature gradient over the surface of the, piston and cylinder. This, actually, temperature gradient causes to damage the, actually engine. So because of these two main drawbacks, we prefer to use the optimum value for compression ratio. And so the other one is the specific heats, correct? We just discussed that, we prefer the highest, actually, the higher K value means, the higher, you know, uh, thermal efficiency. Here you can see, the thermal efficiency versus the compression ratio for different, gases with different, specific, actually, heat ratio with a different K. So as you can see, the higher K means, the higher thermal efficiency. But normally we don't have too much control, on this parameter because you need to use air for the, combustion, correct? So we don't have too much control, on this, actually parameter. And so here is, so what's the conclusion? The conclusion is that, although we prefer to use the actually highest values of R and, K to increase the thermal efficiency, there is an optimum value. We have a limit for the, values of K and R. And then here we can see, the relationship between net power and network. Sometimes you calculate, actually, you calculate the work, based on, the first thermodynamic law. You can calculate the work, and then you may ask to just calculate the power. So if you ask to calculate the power, you can calculate first the network, and then you can use this equation to just convert the W net to the power. You need to multiply the W net by N dot, which is the revolution per minute, and then divided it by N, which is the number of revolution per cycle. And then here is the summary, guys. To calculate the efficiency, the thermal efficiency of Otto cycles, you learn three different, equations. This is very important, guys. You can use the first equation to calculate the thermal efficiency of Otto cycle with constant and variable specific heats. This one, the first one. However, the second one and the third one are valid for the thermal to calculate the thermal efficiency of Otto cycles with constant specific heats. With constant specific heats. So these two equations are for the you know ideal Otto cycle with constant specific heat. The first one is for both constant and variable specific heat. This is very common mistake, guys. I see it, in all exams. So a student use, for example, these two equations to calculate the thermal efficiency of Otto cycles with variable specific heat. These two equations are not valid for ideal Otto cycle with variable specific heat. If you have a variable specific heat, you must use these equations to calculate the thermal efficiency. The first one, correct? Again, the first one is valid for both constant and variable specific heats. The second and third one are just valid for Otto cycles with variable specific hits. And so I will solve two examples next lecture. Please go over this material, and then we'll go over two examples next lecture. Thank you so much and have a great day.